In this video, I'm going to find the eigenvalues, the eigenvectors, and generalized eigenvectors, if any, of the matrix A below. And notice I've put a parentheses S after each quantity because we don't know how many there will be. And so it turns out that there will be a twist to this problem, and that's the reason why I've made this video, because I've never seen a question like this in a textbook. So also, if you need more motivation as to why we would want to compute these quantities, then here's this question below, where we're solving a system of differential equations. And it turns out that one way to solve it is to use the eigenvalues and eigenvectors and generalized eigenvectors, if any, of A. So I'll give the solution towards the end of this video, but we'll see what happens. Alright, so just as a reminder, if we let A be an n by n matrix, and if there exists a non-zero vector v and a scalar lambda such that AV equals lambda v, then we call lambda an eigenvalue of A with associated eigenvector v. Right? So as an example, if we let A be the matrix 1, 2, 2, 1, then we can consider A times the vector 2, negative 3. This gives us negative 4, 1, which is not a scalar multiple of 2, negative 3 for any lambda. So this means that 2, negative 3 is not an eigenvector of A. Now if we consider the product A times the vector 1, 1, then we get 3, 3, which is 3 times the original vector 1, 1. So 1, 1 is an eigenvector of A. We can also view these results graphically. So if we plot the vector 2, negative 3, then multiplication by A on the left, it not only stretches this vector, but it rotates it to give us the vector negative 4, 1. While the vector 1, 1, if we multiply A by that on the left, then we get the vector 3, 3. So you notice multiplication by A, it only stretches the vector 1, 1. It doesn't rotate it at all, right? And that's what this equation AV equals lambda V, it means. So multiplication by A, all you're doing is you're just stretching the vector, right? There's no rotation at all. One last bit of review for finding the eigenvalues. So let's start off with the equation that we were given in the definition. And in fact, this is the only equation that we have to work with. So if we algebraically manipulate this, we can get it to look the following way. And remember, V is an eigenvector, which by definition is a non-zero vector. So this system of equations has a non-trivial solution if and only if the determinant of A minus lambda I is equal to 0. Okay, so now actually to our example that we want to find the eigenvalues, eigenvectors, all that stuff for. All right, so let's find the determinant of this matrix, and let's take advantage of the 2 zeros in the first column by expanding down the first column, right? So the determinant is equal to this, and after some algebra, foiling and then factoring this polynomial, we see that this is how it factors, and that there's only one distinct eigenvalue, which is 3. Okay, so now for finding the eigenvectors, right, we're considering this linear system of equations, so we know that lambda equals 3, so A minus now 3i times V equals 0. Right, so let's use Gaussian elimination to solve this, and notice the 0, right, that vector. So since this is the 0 vector, no matter how many elementary row operations you perform, this column, the augmented column, right, is 0 and will always be 0, right? So it's sort of meaningless to always write that. So we just care about the coefficient matrix, that is A minus 3i. Okay, and it's pretty easy to see that when you put this in echelon form, you get the following. I've written the elementary row operations there just in case you need them. And since elementary row operations don't change the solution set of a linear system of equations, we know that the solution set of this original system is equal to the solution set of this new system, which we previously found. Okay, so V is a 3 by 1 vector. You call its entries whatever you want. I choose to call them A, B, and C. Now, in this last system, the first row tells us that B minus C is equal to 0, or in other words, B is equal to C, right? And A and C are free, right? I could have also said that A and B were free, and that C is equal to B. The important thing is you have two free variables, right? So any and every eigenvector of A will have this form, A, C, C. And I can write this vector in parametric form as A times the vector 1, 0, 0 plus C times the vector 0, 1, 1. And just as a bonus, we can also graph the eigenspace, which is a plane with the equation B equals C. And it's called the eigenspace of the matrix A because a vector drawn from the origin to any point on this plane will always be an eigenvector of A. Okay, so we've seen that there's infinitely many eigenvectors, but there's only two linearly independent eigenvectors. And this is because, again, we have two free variables, A and C. So to make things easy, let's just choose the eigenvectors v1 and v2 to be the vectors that showed up in the parametric form for v. Right? Okay, so now, since A is a 3 by 3 matrix, and we only have two linearly independent eigenvectors, we have to find a generalized eigenvector, and we'll call that vector v3. Now the question is, do you base it off of v1 or do you base it off of v2? Okay, so let's, for starters, just try v1, right? So again, this is a linear system of equations. I'm going to use Gaussian elimination to find a solution. And notice this is an augmented matrix because, you know, this is equal to v1 on the right. It's not equal to the 0 vector, right? And v1 is not the 0 vector. Okay, so if you do some elementary row operations, you see that this, you know, the solution set it's equivalent to this matrix, right? But there's a problem because these last two equations, which are really just the same, they would imply that 0 equals 2, right? And obviously this is a contradiction. This is nonsense. So you can't base v3 off of v1. Okay, so let's try v2. But again, you know, using elementary row operations, we get a similar situation, right? This would imply that 0 is equal to 1. Right, which again is a contradiction. Okay, so now the thing is, right, does a generalized eigenvector even exist? Right, because we can't base it off of v1 or v2. Like, did I make a mistake here, or is the theory wrong, or what? You know, that's why I made this video, because I haven't seen an example like this. It's probably out there somewhere in a textbook, but I haven't found one. It's nice. This is a challenging. I think this is a challenging undergraduate problem. So it makes you think, right? So no, the theory is not wrong. You just have to choose v1 or v2, you know, differently in order to base v3 off of, right? So let's just choose v1, right? So we'll end up choosing a different v1. Okay, but the question is, what does it really mean for this system to even have a solution, right? So let's write it out. Again, v3 is a 3 by 1 matrix, 3 by 1 vector. You can call the entries whatever you want. I'm choosing to call them a3, b3, c3. Right? All right. So instead of viewing this as a matrix equation, let's view this as a vector equation. Right? And the reason why is because what was on the left-hand side of that equation, notice this is equal to the column span of that matrix, A minus 3i. Right? If I go back, right, A minus 3i is that matrix right there. Okay. Now going forward, right, so this is equal to the column span of this matrix, like literally just the span of the columns, right? Because that's how matrix multiplication works. So anyway, this is equal to the span of just the single vector 1, negative 2, negative 2, right? This is obvious because if you take 0 times this vector, you get the 0 vector. If you take negative 1 times this vector, you get the third vector listed above. So the reason why I considered that matrix equation now as a vector equation is to hopefully convince you that this linear system of equations, it has a solution if v1 is in the column space of A minus 3i, right? So for instance, take the left-hand side of this equation, right? You have a matrix times a vector, which at the end of the day is a vector, but that vector is literally equal to the linear combination of these three vectors that we see up here, right? Like it's literally just equal to, you know, a linear combination of the columns of A, right? And if that's supposed to be equal to v1, then that means that v1 must be in the column space of that matrix, A minus 3i, right? Okay, now again, recall that any and every eigenvector of A has this form. So the question is, Can you find a v1 that's of this form that will be in the column space of a minus 3i? And the column space of a minus 3i, it's just equal to the span of this vector 1, negative 2, negative 2. Right? So it turns out you can find a matrix, a vector of this form, right? So if you choose a as 1, c is negative 2, right? Then we can choose v1 to be the vector 1, negative 2, negative 2. All right, which that's in the column space of a minus 3i. Right? Okay, and then lastly, for v2, let's just keep things simple. Let's choose 1, 0, 0. Back to v1. So since we chose it such that it is in the column space of a minus 3i, we're guaranteed that this system has a solution. Right? So again, if you write the augmented matrix, perform some elementary row operations, you get that, you get this relationship between B3 and C3, right? So the top row, that's the only row that has any information. It tells you that B3 is equal to 1 plus C3. And A3 is free, right? So we have two free variables. Let's write this vector in parametric form. And now any vector of this form will be a generalized eigenvector for A, right? So again, to keep things simple, we can actually choose the free variables to be 0 in this case, because the resulting vector will not be the 0 vector. It will be the vector 0, 1, 0. And at this point, we've answered the three questions that I originally asked for this matrix A. Right? So we found that it only has one distinct eigenvalue, which is 3. It has only two linearly independent eigenvectors. Right? I could have chosen a bunch of them, but here's just two of them. Right? And then there's only one generalized eigenvector v3. And this eigenvector v3, remember we based it off of v1. So there we have it. I do have three closing remarks that I'd like to make. The first is with regards to the, I guess, sort of like the motivation example that I listed at the beginning of this video, right? So I said find the general solution to this system of differential equations, right? Where this coefficient matrix, that's the matrix A for us, right? So it turns out that the solution is equal to this. So for this part, I'm expecting that you've seen the eigenvalue method covered in a differential equations class. If you haven't, the solution is still equal to this, but you might just have to do some extra work to understand why this is the solution. But anyway, more explicitly, we can write it in the following way, right? So, and actually, you could even write it as just one vector, right? So this vector x, it's a 3x1 vector. Here's its entries. x1 is a function of t, so is x2 and x3, right? So for instance, if you wanted to find exactly what x1 of t is, right, this is the first entry of the vector. So what you'd have to do is just combine all the first entries of the vectors that you see above, right? So you'll get this. And then, of course, if you do the same for x2 and x3, this is what you get as well. And just in case you don't believe me, we can also check this with computer. I mean, you could check it by hand or you could check it by computer, right? So here I'm using Mathematica, right? So remember, we have x prime is equal to ax. A is this matrix, and x is this vector. Remember, x1 is short for x1 of t. I just didn't feel like writing it a bunch of times. Anyway, if you compute this matrix times vector multiplication, you get this vector, right? So, how do I test if a function is a solution to a differential equation? You just plug it in, see if the left-hand side is equal to the right-hand side. Or in this case, this vector, the first entry is x1 prime. So is x1 prime equal to this? That's the same thing as saying, is x1 minus all of this, right? Minus all of this, if it's equal to 0, right? So if I define these functions, and then I ask it to calculate this, I should get 3 zeros. And I do, right? So it is a solution. I haven't lied to you. Moving on to the second remark, this deals with whether or not you can diagonalize the matrix A. So first of all, it is not diagonalizable because it only has 2 linearly independent eigenvectors. If it had 3 linearly independent eigenvectors, then it would be diagonalizable, but it's not. Right? It's kind of like you can almost diagonalize it. So here's what I mean. If you let P be this matrix where the columns are v1, v3, v2, so explicitly it's equal to that. Then P inverse, it exists. And if you let J be this matrix, right? So it's almost diagonal except for the one that's above the middle 3. And notice the diagonal entries, they're the eigenvalues, or really just eigenvalue of A, since it only has one distinct one, which remember that was 3. Right? So if you define these matrices, then it turns out that Pj P inverse is equal to the matrix A. Right? So this is one way to sort of like decompose the matrix A. I'm not going to explain why this is true. If you want to know why, then you can look up the Jordan canonical form of a matrix. That's why the almost diagonal matrix is, I've labeled it J. That is the Jordan canonical form for the matrix A. And for my last remark, it answers a question which I have been asked a lot when I've been a TA for a class where you talk about generalized eigenvectors, right? So the question is it possible to base the generalized eigenvector v3 off of both the eigenvectors v1 and v2, right? Because there is a choice, right? When you find v3, do you base it off of v1 or v2? So we chose v1 such that you can base v3 off of it. I could have labeled v1 as v2, right? So, but the question is, could you do it for both? And the answer is no, right? So here's why. Remember that this system, it has a solution if and only if V is in the column space of A minus 3i. Now that matrix A minus 3i, it's equal to that one, and the column space of that matrix, it's just equal to the span of 1, negative 2, negative 2. Again, I mentioned y before. Right? Okay. So to show that the answer is no, suppose by contradiction that the answer is yes, right? That you could base it off of both v1 and v2, right? So then by the argument or by the reasoning above, right? v1 and v2, they would both have to be in the span of that vector, right? So we can say v1 is some alpha times that vector. Similarly, v2 is some beta times this vector for non-zero constants alpha and beta. And why are they non-zero? Again, that's because eigenvectors are non-zero vectors, right? So if alpha was 0, then v1 would be 0. That's a contradiction because you're right, every eigenvector has to be a non-zero vector. Okay. So since alpha is not equal to 0, consider the product of 1 over alpha times the vector v1. It's equal to this. And through some algebraic manipulation, we find out that this is actually equal to 1 over beta times the vector v2. Right? So in this chain of equalities, I want to equate these two things that I've circled. Right? And we see that v1 is a scalar multiple of v2. And so that means that v1 and v2 are linearly dependent. This is a contradiction, right? Because eigenvectors must be linearly, well, the eigenvectors that we chose, v1 and v2, they had to be linearly independent, right? But if you assume that that v3 can be based off of both v1 and v2, right? Then like we said, that means both of those vectors have to be in the column space. The column space is just spanned by one vector, right? So if they're both in the column space spanned by one vector, that means that they're scalar multiples of that same vector, right? So in other words, they're scalar multiples of each other because also, again, they can't be the 0 vector, right? That means they're linearly independent, so there's your contradiction, right? So v3, it can only be based off of one eigenvector, not both. And which eigenvector it can be based off of? Well, that's just a labeling game, right? We chose v1. I could have labeled v2 as v1, and then you can base it off of v2, right? But you can't base it off of both v1 and v2. All right. So I hope you enjoyed that video. Thanks for watching. If you made it this far, I appreciate it. I'll see you later.